Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is circuit protection devices. Our objective today is to take a close look at basic circuit protection devices. We'll introduce fuses, circuit breakers, overloads, and ground fault current interrupters and discuss their intended purposes, means of operation, and the differences between them. Circuit protection devices are components that safeguard people and property from electrical and fire hazards. You are a circuit protection device. The simple act of just not doing stupid things is the first and most important line of defense when it comes to circuit protection. It is my intention that you understand, appreciate, and respect electricity, not fear it. It is as dangerous as it is useful, and there are laws, natural and man-made, that govern its wise use. Follow the rules. Follow the code. The National Electrical Code is there to safeguard people and property from electrical and fire hazards. Pay attention and do not operate devices outside their intended range, nor excessively overload them for sustained periods of time. If this advice is to be boiled down into a single standing order, let it be this: watch the current. Given our understanding of the power equation, we realize that power dissipated by a device is proportional to the square of the current going through it. It is therefore understandable that it is of primary importance to maintain current at or below a certain predetermined level, since any increase in current constitutes a geometric increase in power dissipation. This is where not only a conceptual understanding of electrical theory comes into play, but also proper instrumentation use and the interpretation of numerical results. It is incumbent upon any individual using any expensive electrical apparatus they wish to keep in working order to continually monitor current. For reasons I'll explain later, an overloaded or stalled motor will draw excessive current. The excessive current will heat up the wires. The hot wires will melt the electrical insulation or ignite it. The exposed conductors will cause more problems and more fires in an ever-increasingly bad positive feedback loop. Even with no circuit protection devices, such a situation is totally avoidable if you know how to use common electrical instrumentation and interpret numbers. Avoid high current for sustained lengths of time. Pay attention and be prepared to shut it down any moment you observe unusually high current for a sustained period of time, smell or see smoke, or worse yet, see flames shooting from the system you're working on. Know where the off button is and make sure you've got access to it. Industrial systems often have strategically placed emergency stop buttons that allow an individual observing an unsafe action or scenario to immediately disable the system. Familiarize yourself with the location of these switches and know their intended purpose. Modern systems, however, cannot rely upon near constant human intervention. It is for this reason automatic circuit protection devices are employed. Additionally, I don't mean to discount preparedness, but I do need to temper your expectations, because things do go wrong to even well-prepared people. Understanding basic electronics theory does not grant you invincibility. No amount of conceptual preparation can prevent a faulted component from igniting the moment the power is turned on, nor can it prevent you from receiving an electrical shock from an exposed wire. The job of circuit protection devices is to prevent such problems from becoming injuries or damaging equipment. Today we'll take a brief look at fuses, circuit breakers, overloads, and ground fault current interrupters. All different types of circuit protection devices that all basically do the same thing. They open up and stop current flow just like an emergency off switch. They use different means of detection and operation, but ultimately they perform the same function. They stop current flow. Circuit protection devices are always placed in series with the electrical load they intended to protect, because elements in series with one another carry the same current. This is the most basic of series properties, and protection devices make use of this fact to selectively enable or disable current flow. If a circuit protection device is closed, it allows current flow to the load, whereas an open protection device does not. Some of these devices you might already be familiar with just from general exposure. Fuses are commonly found in automobiles or old houses. Circuit breakers are most likely found in an electrical panel servicing a modern residence. Ground fault current interrupters are funny-looking outlets that might be found in your garage, bathroom, or kitchen. We'll look at each one in turn and discuss how they protect electrical devices and operators from hazards. Fuses. A fuse is a metal alloy element that is purposely designed to melt at a specific temperature and open the circuit. Here's the common schematic symbol for a fuse. It is a two-terminal device that is placed in series or in line with a load it is intended to protect. A fuse has a body, inside which the metal alloy element is soldered or welded to the contacts. End caps, called ferrules, or sometimes blades. Sometimes the body is glass or transparent plastic, and you can see the metal alloy element. Sometimes the body is opaque and filled with a quartz sand filler, for reasons I'll return to in a moment. When the fuse is intact, the path between its two terminals is a closed 0 ohm path, and the circuit operates as intended. When opposition decreases and current reaches or exceeds a certain predetermined value for a certain amount of time, the fuse melts, and the path between its two terminals opens and stops current flow by becoming an infinite resistance. The fuse is essentially acting just like a switch in series with the electrical device it is intended to protect. If the switch is closed, current will flow. If the switch is open, current will not flow. Fuses, however, differ from traditional switches in that fuses are one-time use only. When a fuse blows, it is rendered inoperable, and here's the important part. Once the fault that caused the blown fuse has been identified and rectified, the damaged fuse must be replaced with a functional fuse with the correct rating. Fuses have 5 common properties: rated current, time delay, rated voltage, breaking or interrupting capacity, and rejection type. We'll briefly discuss each property. Rated current. As mentioned previously, the business end of a fuse is a metal alloy strip that quite literally melts when current in excess of its rating travels through it. When you need to protect your circuit against a draw in excess of 3 amperes, you specify a fuse with a current rating of 3 amperes. Again, follow the NEC guidelines for determining the recommended fuse size. Time delay. Depending upon the composition of the metal alloy element, this opening action could happen quickly in the case of a fast blow fuse, or take a measurable amount of time to do so for a slow blow fuse. Recall that motors can exhibit a phenomenon called inrush current, in which an intense but brief draw of current occurs when a motor is first started. Inrush currents can sometimes be in excess of 6 times regular operating current. A slow blow fuse is often used in series with a motor supply voltage by allowing the temporary passage of such high current, but sensing sustained current draw, the fuse will blow after a predetermined time. The time-delayed action of a slow blow fuse is a heat transfer relationship between current and time. The higher the current, the faster the fuse will blow. The lower the current, the slower the fuse will blow. Ideally, the inrush current for a motor and a properly sized time delay fuse will be quick enough to prevent the time delay fuse from blowing. Rated voltage. In addition to a rated current, a fuse has a rated voltage, which indicates the maximum safe operational voltage limit. Larger voltages require physically larger fuses to interrupt the same amount of current, because even air could become a conductor with a dangerous arc forming between 2 high voltage points in close proximity. Breaking or interrupting capacity. Fuses also have what is known as a breaking or interrupting capacity, which is the maximum current that can be safely interrupted by the fuse. The breaking capacity should be higher than what the power supply is capable of producing during the event of a short circuit. Rejection type. Finally, some fuses are designated as rejection type fuses in that physical modification of one of the 2 terminals comprising the fuse makes it impossible to insert a fuse with a different rating in the same fuse holder or similarly a fuse block. This is accomplished with an annular indent on the ferrule of some fuses or a slot cut into the blade of others. The dimensions of the annular indent or slot do not allow an improperly rated fuse to be inserted into the same fuse holder or fuse block. Here's a non-rejection type fuse being employed in a fuse block. Note the flat and featureless ferrules. Here's another fuse block designed to hold a rejection type fuse. Here's a rejection type fuse that's being placed into a fuse holder improperly. The fuse holder won't close because that's not the way a rejection type fuse is inserted. Only when a fuse of the proper type is inserted correctly will the fuse holder close. Quick note about fuse holders. Do not open them while the system is operational. They are not intended to be on and off switches. Recall that even air can be considered a conductor between 2 high voltage points in close proximity. A purposely designed means of disconnection accounts for this possibility by providing a means of quickly extinguishing any arc that may form between 2 points. As we'll learn later, circuit breakers and contactors designed for this purpose employ some pretty exotic means of doing so. Once the system is properly shut down and properly locked and tagged out, only then can the fuse holder be opened and the fuse inspected and/or replaced. In addition to following proper lockout and tagout procedures, by keeping the fuses with you while you perform a maintenance procedure establishes yet another layer of protection, preventing the inadvertent startup of equipment. The advantage of fuses is their incredibly simple operation principle. As long as the rated voltage and breaking capacity of the fuse is appropriate for the application, they are an inexpensive and reliable means of defense. This being said, a blown fuse is a non-reusable component. Following safe work procedures, the system must be locked out and tagged out, the error that caused the high current removed, and the old fuse must be removed and replaced with a new one if this system is to operate again. In short, replacement requires intervention, and it is sometimes not a simple process. Because of this disadvantage, fuses often form the final but most reliable line of defense for circuit protection. If there is a line that absolutely must not be crossed, a fuse is there to figuratively burn down the bridge prior to letting the whole castle burn down. The metal innards of the fuse are sometimes packaged in glass cartridges or plastic blades for automotive applications. These transparent cases make inspection of the fuse incredibly easy. You just look at it. If the metal strip inside is melted, the fuse is blown. If the metal strip inside is intact, the fuse is most likely good. Here's a couple automotive fuses. Notice the metal strip forming the acting element for the green 30 ampere fuse is physically larger than the blue 15 amp fuse. It makes sense. A 30 amp fuse needs to carry more current before it melts than a 15 amp fuse. In this case, both these fuses are intact. Here's a couple glass-bodied fuses, both of which are 1 amp, 250 volt rated fuses. Notice the different physical dimensions. You can't fit a 6 by 32 millimeter fuse into a fuse holder made for a 5 by 20 millimeter fuse any easier than you can fit a 5 by 20 millimeter fuse into a fuse holder made for a 6 by 32 millimeter fuse. The thin wire forming the acting element is representative of the current rating of the fuse. The element inside a fuse designed to blow at 2 amps will be thicker than one designed to blow at 250 milliamperes or 0.25 amps. Again, the transparent housing of these types of fuses makes inspection really easy. You just look at it. Sometimes it's not that easy, because often the metal alloy element is covered with an opaque body covered with a filler. The filler, often quartz sand, is used to dissipate the heat in the fuse below the rated current, and in the event of excess current, the sand is there to quench the arc that may form between the two terminals. Here's a big old bladed fuse. This guy is a 500 ampere rated fuse that is rated for 600 volts AC and only 300 volts DC. It has an interrupting capacity of 300 kiloamps AC and 100 kiloamps DC. Here's another fuse. It's a rejection type fuse with ferrules. It has a rated current of 5 amperes, a rated voltage of 600 volts AC and 300 volts DC. It has an interrupting capacity of 200 kiloamps AC and 100 kiloamps DC. If the fuse is suspect or cannot be visually inspected, as is often the case, one can step beyond the visual range and use an ohm meter to check continuity. An ideal fuse has 0 ohms of resistance, although real fuses will exhibit some tiny amount. A blown fuse should exhibit extremely high resistance. Here are 2 fuses, one of which is operable and the other inoperable. Which one is blown? It's obviously the one with a red band, because I wouldn't be so dumb as to keep an inoperable fuse laying around the lab. That would be the source of all sorts of confusion. Get it? Confusion. This is a teaching aid, but let's say they're both externally indistinguishable. The good one shows continuity between its 2 ends. This fuse is good. The blown fuse with the red band shows over limit or extremely high resistance between its 2 ends. This fuse is blown. If this is a troubleshooting scenario, the fuse is not at fault. The fuse did its job. It sacrificed itself so the rest of the circuit could live to fight another day. The cause of the high current event must be investigated and resolved before a replacement fuse is inserted. If the error was still present, the new fuse would follow its predecessor over the cliff. If a system is continually blowing fuses, you're wasting money and time feeding it more fuses. Fix the problem. Do not think for a moment that inserting a fuse with a higher current rating is an acceptable solution to this problem. Current in the circuit will reach this higher, potentially more dangerous current, and then the fuse will blow again. Additionally, do not think by jumping or bypassing the fuse with the wire will the system function as intended. Without circuit protection, the system will burn itself to the ground. Circuit protection exists for a reason. It is not to be bypassed. There's not a lot more to say about fuses except this. Fuses are non-reusable devices designed to protect the system from high current. They do not protect operators from leakage current. Allow me to demonstrate. Consider a 1/4 horsepower motor designed to operate on 120 volts, protected by a 3 amp fuse in series with it. Let's say this motor is 90% efficient. Recall from the efficiency lecture, available at the Big Bad Tech channel, that efficiency is the ratio of usable output obtained from a certain input. A 1/4 horsepower motor will produce a 1/4 horsepower output. Big surprise when drawing its rated current. If 1 horsepower equals 746 watts, 1/4 horsepower equals 746 watts divided by 4, or 186.5 watts of usable output. What is the necessary power input, and what is the rated current for this motor supplied by a 120 volt source? Solving for power input, we find output divided by efficiency. Substituting in the necessary values, we find approximately 207.2 watts must have come into the motor for it to deliver its required output. Given power is equal to voltage times current, and solving for current, substituting in the necessary values, we find this motor must draw roughly 1.7 amps of current from the source to deliver its rated power. The 3 amp fuse in series with this motor allows this level of current draw, and only anything in excess of 3 amps will cause the fuse to blow. That's the point. A large current draw will damage the motor, and replacing a fuse is less expensive than replacing a motor. The fuse only functions when current draw is in excess of 3 amps. Recall from the electrical safety lecture, available at the Big Bad Tech channel, that it does not take a lot of current to kill or injure you if you take that current through especially vulnerable and valuable portions of your anatomy. Let's say your lab partner takes this motor with them into the bathtub. They plug it into an outlet and start taking it apart. Yes, this visualization is making me cringe too, and it's not the impending electrocution hazard that is making me sick. Let's start again. Let's say your fully clothed lab partner takes this motor into the bathtub with them. They plug it into an outlet and start taking it apart. Let's say their wet body presents an unusually low resistance path of 4 kiloohms. Any contact with an energized 120 volt conductor in this motor places their body in parallel to 120 volts. The motor continues to draw its rated current of roughly 1.7 amps, and their body now draws additional current in the amount of 30 milliamperes, an amount of current sufficient to deliver some serious damage to the human body. The 3 amp rated fuse is therefore passing roughly 1.7 amps plus the comparatively small amount of 30 milliamperes of current through it for a total of 1.73 amps. The 3 amp rated fuse does not blow because the current draw, although dangerous and deadly to the operator, is well inside its operational range. We'll discuss a means of protecting operators from small leakage currents when we discuss the ground fault current interrupter, but understand a fuse does not offer this level of protection. As a brief preview of the ground fault current interrupter, consider the outgoing and incoming current during normal and faulted operation. In normal operation, the incoming current to the source is equal to the outgoing current. In faulted operation, the incoming current is less than the outgoing current because the small leakage isn't returning through the intended path. Circuit breakers. Moving on to our next circuit protection device, let's briefly discuss the circuit breaker. A circuit breaker is a circuit protection device very similar to a switch, in that it is a 0 ohm resistor becomes an open or infinite resistance if current gets too high. Here's the schematic symbol for a circuit breaker. Sometimes you'll see the sensory apparatus used to detect excessive current draw placed in series with a circuit breaker. These are magnetic trip units. These are thermal trip units. For operation with a single source, it is essentially a 2-terminal device placed in series or in line with the load it is intended to protect. Industrial power isn't normally limited to single sources, so sometimes you'll see 3-phase circuit breaker. It's essentially the same thing as 3 2-terminal single-phase circuit breakers all linked together. We'll discuss the details of three-phase AC later, but proper operation of a three-phase system normally requires a balance between the three independent sources. Consider the coordination offered by a single three-phase circuit breaker and contrast it to three independent fuses servicing three individual phases. The circuit breaker is a single point of control that opens or closes all three sources simultaneously. The fuse is not so much. One fuse could blow, and the other two fuses still function, leading to an undesirable upsetting of the balance between the three separate phases, known as single phasing. Single phasing is normally associated with high current draw, reduced performance, and a uniquely horrible sound produced by a three-phase motor. Circuit breakers operate similar to switches, even more so than fuses, because circuit breakers can be reused and reclosed after they've opened. When the circuit breaker is closed, the circuit operates as intended. When the opposition decreases and current reaches a certain predetermined value for a certain amount of time, the circuit breaker trips or pops, and the switch opens and stops current flow. In contrast to fuses, though, after the error that induced the high current has been cleared, the circuit breaker can be simply reset without the need to purchase another expendable item. Similar ratings, such as rated current, rated voltage, and interrupt rating exist for circuit breakers as they did with fuses. As mentioned previously, the circuit breaker can detect the high current condition via several different methods, but the most common ones is via thermal or magnetic means. Sometimes the schematic symbol will incorporate those methodologies. We don't necessarily need to go into details about the detection mechanisms and actuation right now, but realize a circuit breaker's contacts are moving parts. This means that a circuit breaker is a far more complicated system than a fuse, which is essentially a piece of metal that just melts. For extreme cases, fuses and circuit breakers can both be paired in series with the element they intend to protect. In this case, the circuit breaker should have a rated current below that of the fuse. In the event of an overcurrent event, the reusable circuit breaker should trip first and open. If the circuit breaker fails to open, the overcurrent event approaches that of the fuse rating, which then melts. This double layer of protection uses the reliable fuse to back up the reusable circuit breaker. Here's a three-phase circuit breaker removed from a circuit. In its closed position, the L1 to T1 terminals present almost no opposition to current. When it's automatically or manually tripped, it opens and forms a large resistance through which no current can flow. Unlike the fuse, though, the circuit breaker can be reset into its closed position. Here's a video clip of the switching action. Notice the sound which the circuit breaker makes. It's a satisfying snap, and you can really feel a jolt when actuating it. This is one of the arc extinguishing means I referred to earlier. There's basically a spring on the moving contacts, and when actuated rips the contacts apart, like a referee at a fight, and sends them to their respective corners. This rapid and forceful separation means that the arc that could potentially form between these contacts is given less of a chance to do so. Additional precautions are often used to minimize this arc. Larger circuit breakers use arc chutes to divide and cool the arc. Blowout coils or other magnetic means deflect the arc into the arc chute. Gases with a strong dielectric strength, a property we'll discuss later, like sulfur hexafluoride, SF6, quench the arc in gas circuit breakers. Vacuum circuit breakers have nothing inside them to ionize in the first place, and the arc is extinguished upon opening. Opposite to this methodology is an air circuit breaker, which uses compressed air to blow out the arc like a giant birthday candle. All these methods share the same goal. They terminate arc current very quickly. Typically, the arc is extinguished between 30 and 150 milliseconds after the mechanism has been tripped, depending upon the age and construction of the device. As we'll soon discuss in the basic parallel circuit properties lecture, circuit breakers are often used to functionally isolate sub-circuits inside a larger system. Only those circuits that are exclusively fed by that circuit breaker are affected, allowing other portions of the system to run if needed. For example, the main circuit breaker, servicing a residence, affects all circuits, whereas the circuit breaker associated with just some bedroom ideally services only that bedroom. This allows other vital systems to function while you perform maintenance on the electrical system in that bedroom. Before we move on to our next protection device, consider again the means of operation and purpose of a circuit breaker. It protects the system from high current. It does not protect an operator from small levels of leakage current. The only way a 20 amp circuit breaker will open is if it is manually open or automatically tripped when an excess of 20 amperes of current is traveling through it. Overloads. Realize both the fuse and the circuit breaker protect against big extreme short circuit events. For any of you that have trained for an athletic event before, you're aware cumulative overtraining can be just as damaging as a big fight or a hard race. What I'm referring to is overload situations. Events that have spaced over time would ordinarily be no cause for concern, but become extremely hazardous if continually experienced. The conductors supplying electrical devices like motors are sized given certain operating conditions and incorporate significant safety factors as dictated by the National Electrical Code. This safety margin is only applicable if you operate the system close to as it was intended. If an undersized motor is continually being asked to drive oversized loads, it is operating in overload conditions. Overload means the device is drawing in excess of normal current, but perhaps inside the range of the chosen fuse or circuit breaker rating. Over time, an excess draw of current may increase the temperature and degrade the insulation surrounding the conductor. If sustained, this condition could create a fire hazard. An example of an overload condition might be an electric saw hitting a knot in a piece of wood or your electric car making a steep climb. If the circuit breaker was undersized, the system would experience what is called nuisance tripping, and every time you hit a knot or went up a hill, the whole system would stop and need to be reset. Not the most ideal of situations when saws are routinely asked to cut through imperfections and cars are routinely driven up hills. Overload conditions only become harmful if they're sustained, for example, the locked rotor on a motor. It is for this reason we'll introduce the third circuit protection device known as an overload, or alternately, an overload relay or a thermal overload that protects from sustained overload conditions. This is the key. An overload protects against damage from sustained overload conditions. It will allow a motor or other device to overload, but only for a given amount of time before it also opens the circuit. This allows our device to operate above and beyond normal requirements for a brief amount of time, but interrupts the circuit if such conditions become damaging. Motor starters and relays are a little outside the scope of our present level of understanding, and we will return for a more thorough discussion of these concepts and devices later when we move into the motor controls series. However, I would like to touch on just the basics of motor starters and overload relays, because they're pretty neat devices. I'm going to have to make some gross simplifications now, which in retrospect you probably laugh at when we have a thorough understanding of motor control much later. Let's start off with a discussion about a three-phase motor starter. This is a device that incorporates not only a circuit breaker, but also overloads. Here's the schematic symbol for such a device. Everything is integrated into a single package inside this brown box. Here's the circuit breaker. Here's the means of manually activating the circuit breaker. Here are the thermal overloads in series with the circuit breaker. Here's the magnetic current sensors. Notice the circuit breaker servicing all three phases can be activated via three different methods. Method 1, you can manually open or close it. Method 2, the magnetic current sensors can open or close it in the event of a short circuit or unusually high current draw, just like a traditional circuit breaker. Method 3, the thermal overloads can open the circuit breaker in the event of a sustained current draw. What is interesting to note for this integrated package is that neither the thermal overloads nor the magnetic current sensors open. The only reason these devices are here is to tell the circuit breaker when to open. The thermal overload is a sensing device. A purposely built interrupting device must make or break the circuit. We'll return to this important fact in a moment after we take a brief look at a motor starter with this integrated package. Here's a three-phase motor starter. It is essentially a set of three switches. The dial on the front adjusts the current at which the thermal overloads actuate. If this setting was incorrect, the overload would not function as intended, perhaps trip early, or worse yet, not at all. When manually, thermally, or magnetically tripped open, an ohm meter indicates there is no connection between the L1 and the T1 terminals. When closed, an ohm meter indicates there is a connection between the L1 and T1 terminals. The manual knob can be placed in the open condition and a slider pulled out to allow a convenient method of lockout and tagout. Let us now talk about a different device, the overload relay. In contrast to the motor starter, which physically incorporates the thermal overload sensory elements inside it. An overload relay is a physically separate device that, similarly to a motor starter, tells a purposely built interrupting device to make or break the circuit in the event of overload conditions. In this case, it's telling a contactor, essentially a high current switch, to open or close. Here's the symbol for a contactor. It is not a circuit protection means. The circuit breaker in front of it is. The contactor is rather a means of starting or stopping the motor when you want it to start or stop. What comes after the contactor, yet before the motor, is the overload relay, also in series. Again, the thermal overload symbol is the opposing question marks. The contactor paired with an overload relay is known as a motor starter, similar to our previously integrated package. A motor starter, whether it's integrated into a single package or composed of two separate devices, has a means of connecting the motor to a supply voltage, the contactor, and a means of protecting the motor, the overload. The point is, you need both to be considered a motor starter. Here's where the use of overload relays gets interesting. The contactor closes when some other circuit tells it to. This is the really neat part. The control circuit could be low voltage, low current, and totally electrically isolated from the high voltage, high current motor supply circuit. It's like two totally independent circuits that only interact with each other at certain points, one of them being the contactor, the other point of interaction being the overload. The overload relay, if current draw is below a certain value, allows the motor to continue operating. However, sensing a period of sustained excessive current draw in the high voltage, high current motor circuit interacts with a low voltage, low current control circuit and says, turn off the contactor. This interaction point on the overload relay is known as an auxiliary contact. It's basically a switch, but it only interacts with the control circuit. When the control circuit tells the contactor to open, the contactor opens, and at no time did the overload itself open. Only the contactor opens and closes. The thermal overload is again just a sensory device that interacts with the control circuit via the auxiliary contact. Only after the thermal overloads have cooled and reset will commands from the control circuit allow the contactor to close again. Understand, this is the quickest of explanations, and I don't blame you if you're scratching your head a little. Today's takeaway point about overload relays is this: they are sensory devices only, do not break the circuit in the event of sustained overload conditions. They simply tell another device to do so. Here's a three-phase overload relay. It has three paired overload elements and two auxiliary contacts. The 95 to 96 pair is normally closed. This relay has an adjustable overload setting, quite like our motor starter. If this setting is incorrect, the overload will not function as intended and perhaps trip early, or worse yet, not at all. This overload relay also has a setting that allows for automatic reset after the overload elements have cooled, or another setting, H, think hand, that requires a manual reset. Here is an overload relay that is not triggered. Notice there is connection between the L1 input and the T1 output as indicated by the ohm meter. If I manually test the overload relay, there still exists a connection from L1 to T1. The overload element is not breaking the circuit. If, however, I move my ohm meter to the auxiliary contact, this is where we find the indication of an overload. When the overload is not triggered, this normally closed auxiliary contact from 95 to 96 is closed. When I manually trigger this overload relay, this auxiliary contact opens. This is the interaction point with the control system that indicates it's time to open the contactor. The means overloads used to sense this excessive current draw are pretty creative. One method uses a strip made out of two metals, hence the name bimetallic strip, with two different expansion rates. When heated from excessive current draw, the one side expands and mechanically opens a switch. This is the switch that tells the low voltage control circuit to open the high voltage contactor. If the overload was designed for an exceptionally small device, this switch could also directly open the supply current, but that's not how it's typically done for industrial applications requiring high power. A second method thermal overloads employ uses a metal alloy that passes directly from the solid state to the liquid state at a certain temperature, without a malleable lumpy intermediary. This is called a eutectic mixture. The solid state of this mixture retains the spring-loaded switch, but the liquid state lets the spring-loaded switch move, and this switch is what, again, signals the control system to open the contactor. The third method uses digital means. Think a really small computer to monitor current and signal the control system in the event of a sustained high current. Overloads, regardless of their means of operation, after being triggered, must be reset for this device to operate again. The overload, like the circuit breaker and unlike the fuse, is a reusable device. Sometimes this reset is performed automatically, or it must be done so manually, requiring human intervention. The time period between triggering an automatic reset allows the overload element to cool. Due to the cumulative nature of heat, overloads that have been triggered once will trigger earlier if subjected to the same overload. Repeated overloads are a clear sign the motor is undersized for the task. Do not for a moment think we are done discussing overload relays. We'll return to a far more thorough discussion of motor starters, contactors, and overload relays and more in later lectures on motor controls. For now, an overload is a circuit protection device that allows temporary excessive current draw, yet stops sustained excessive current draw. In contrast, circuit breakers and fuses interrupt extreme current draw, typically associated with short circuits. Ground fault current interrupters. Before we move on to our final protection device, the ground fault current interrupter, we need to discuss the use of ground as a protection mechanism. We'll briefly discuss system and equipment grounding, bonding, and equipment grounding conductors. But before we do so, let me make this important point. I'm as eager to engage in a protracted discussion about NEC regulations as I am to throw stones at an angry hornet's nest. You cannot use anything in this or any other lecture as professional electrical advice. Follow the rules, follow the code. It's there for a reason, to protect people and property from fire and electrical hazards. In addition to its use as a handy reference point, ground actually serves as a means of protecting people from becoming an inadvertent path for electrical current. Intentional grounding is the purposeful introduction of a ground connection to ensure the safety of operators and the proper operation of protection devices like circuit breakers and fuses. Unintentional grounding is a fault condition and needs to be detected and resolved by protection devices. Consider an electrical device enclosed in a conductive frame. This could be a washing machine, a kitchen appliance, a motor, or anything electrical meant to interact with humans. The innards contain the electrically active components and conductors, yet the frame and buttons servicing the machine should be electrically neutral and safe to touch. The negative terminal of the voltage source supplying this device is intentionally grounded, meaning the positive side is referenced from ground. This is one aspect of grounding known as system grounding, meaning the electrical connection of one of the current carrying conductors to ground, in this case, the one leading to the negative terminal. If a conductor servicing the electrical innards of the machine accidentally made contact with a conductive frame, the frame would now also be energized. If the frame did not have a return path to the source, let's say because it's sitting on rubber feet or an insulating pad, it's sitting there like a snake, coiled and waiting, ready to bite the next person that touches it, because that person is now a return path. In effect, this unfortunate person, by touching ground, is closing a switch in parallel to the electrical device and completing a path from positive to negative. This is unintentional grounding and to be avoided. As we learned in the electrical safety lecture, available at the Big Bad Tech channel, it does not require an unusually large amount of current through vulnerable or valuable portions of your body to cause immense pain or even death. As long as the rated current of this circuit breaker servicing this machine is not exceeded, it will not trip despite being an obvious safety hazard. A very simple modification to this device could prevent such an unfortunate occurrence. This simple modification is the other aspect of grounding known as equipment grounding. An extra wire, known as an equipment grounding conductor, is intentionally connected to the device's conductive frame and ground. In this case, the frame is additionally bonded, which is the permanent establishment of a low resistance path to ground for something that normally doesn't carry current. Now, if an uninsulated energized wire did happen to make contact with a conductive frame, there now exists an extremely low resistance path to ground, and the circuit breaker would open when current exceeded its rated value. Additionally, the equipment grounding conductor, by connecting the frame to our reference upon which operators stand, limits something known as the touch voltage to that same ground potential. Bonding the frame to ground purposely creates a low resistance path to ground so overcurrent devices like fuses and circuit breakers can operate, and operators always touch things at the same potential as what they are standing on. Now we can discuss our last protection device, the ground fault current interrupter, otherwise known by its initials GFCI. Key to the operation of the GFCI is the comparison of incoming and outgoing current. At all times, these values should be equal and there should be no leakage current. If a fault condition occurred such that another return path existed to ground besides our intended incoming and outgoing wires, the GFCI detects the imbalance and immediately opens the circuit. Consider this scenario in which a motor is protected by a GFCI. Let's say the motor is drawing 1.7 amps of current from a 120 volt power supply. 1.7 amps is outgoing and 1.7 amps is incoming, and the GFCI does not signal a fault. Now, in clear violation of lockout and tagout procedures, a person standing on the ground reference reaches inside the electrically active device and makes contact with an energized conductor. The person is now in parallel with the positive terminal and ground. Since the positive terminal is referenced to ground via the system grounding, a potential difference exists and additional current can flow out of the positive terminal through the person to ground. Let's say this person is only drawing an additional 30 milliamperes, enough to cause outrageous amounts of pain and serious damage, however, well inside the limits of a traditional circuit breaker supplying this circuit. In this case, 1.7 amps plus 30 milliamperes, or 1.73 amps is outgoing. However, only 1.7 amps is returning via the intentionally grounded conductor. The other 30 milliamperes is leaking through an unintended path to ground. This is an unintentional ground fault. There is now a difference between incoming and outgoing current. The GFCI recognizes this difference and immediately opens up the circuit, as would a traditional circuit breaker. The GFCI is fast-acting, close to the source of the fault, and can detect extremely small imbalances between the two currents. Again, the magnitude of current necessary to cause extreme pain or extreme death is relatively small. The GFCI and proper grounding can detect this small leakage current in unintended paths. This wraps up our discussion of common circuit protection devices. Let's compare and contrast these devices we covered one last time. Both fuses and circuit breakers open when current draws in excess of the rated value. The fuse is expendable and very reliable. A circuit breaker is reusable, yet because of the moving parts is more complicated. An overload device allows brief overloads but protects against sustained overloads. A GFCI detects imbalance between incoming and outgoing current and interrupts the circuit if it detects small amounts of leakage. Finally, and most importantly, you are a circuit protection device. Pay attention to current. Always operate devices inside their intended range and avoid sustained overload conditions. Know where the emergency off switch is and make sure you've got access to it at all times. In conclusion, this lecture took a close look at basic circuit protection devices. We introduced fuses, circuit breakers, overloads, and GFCIs, and discussed their intended purposes, means of operation, and the differences between them. Additionally, we discussed the use of system and equipment grounding, bonding, and equipment grounding conductors used to protect people from electrocution hazards. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.